and this is the yesterday lecture, and we discussed about one of the probably 7-8 applications that uses an op-amp, and one of the most important application is the non-inverting amplifier. To remind you about the non-inverting amplifier, the input signal or the Vin is applied to a non-inverting input, and the feedback network is created by the two resistors, the RF and the RI. The RI, or the notation for the RI, it's like, the input resistance on the inverting input, and the RF, it's from the feedback resistance. You notice that the group of the two resistances, it will return a portion or a fraction of the output signal to the input of the amplifier. And what an amplifier does, again, it will amplify the difference between the two input signals. Means that the V out, it's always the difference between the V in positive or the inverting input and the non-inverting input signal. The other circuit that derives from the non-inverting amplifier, it's the voltage follower. If we are making in this expression the RF as 0 and the RI as infinite, you notice that there is a straight connection between the output and the input, which makes the gain of a voltage follower is equal to 1. Remember that, the gain for a non-inverting amplifier always is a positive value. Again, another way to look for this expression, for this number or dimensionless value for the closed loop for a non-inverting amplifier, is that the input voltage is in phase with the output voltage. Means that there is no phase shift between the two voltages, the output voltage and the input voltage. Now, going back to the other two characteristics or the other two advantages of the non-inverting amplifier, we mentioned that using a feedback, it will increase the input impedance for a non-inverting amplifier. And in this expression, you notice that I'm having, the bracket as 1 plus another, number, which is the gain for an open loop. Again, this gain is provided or is given by the manufacturer. Usually it's a very large number, like 100 or 200. Usually it's around 200 for 741. B is defined as the attenuation or the ratio of the two resistances, the Ri, and the on denominator we have the two resistances, the Ri and the Rf. Remember that this group of the two resistors Rf and the Ri works or it will define the Vf or the feedback voltage, the Vd differential input, or the V plus minus the V minus, it will be amplified by the amplifier. You notice that the input impedance for the non-inverting amplifier is greater than, or it's much greater than, the input impedance of the open loop or the provided impedance from the manufacturer. In the same way, you can look for the other advantage for a a feedback network is the output impedance, or the Z out of a non-inverting amplifier. It's the provided impedance, which is the Z out, which I mentioned that is about 100 ohms, over the same bracket, which is 1 plus the gain of an open loop multiplied by the B. Means that the input or the output impedance for a non-inverting amplifier, it's much smaller than the output impedance for an amplifier that it's working or it's provided by the manufacturer. Means that it's not connected as a non-inverting or an inverting amplifier. Now we are switching to the second. Means that the first two or the first application is using an op-amp as a non-inverting amplifier, and the second important a circuit or application for an op-amp is an inverting amplifier. In this week lab or lab 7, we go through the measurements that we can take using a non-inverting amplifier. As a homework, I used the inverting amplifier, and now we know how to calculate the theoretical value for a non-inverting amplifier. And now we are going over the other application, which is an inverting amplifier. Now, before I'm going to define the gain for a non-inverting amplifier, I have to make some observations. You notice that using an op-amp as an inverting amplifier, the input signal or the Vin is applied to the inverting input. You notice that I'm having that inverting input, or the Vin minus, which is the inverting input, and is going through a resistance Ri. Again, Ri, or the input resistance, and the Rf is the feedback resistance, which is always connected between the output and one of the two inputs. Now, just to go back in the initial characteristics for an op-amp. If you remember, we talk about a very high input resistance. Ideal, it's an infinite resistance, but practically it's a very large resistance. Means that the resistance between the two inputs, the inverting input and the non-inverting input, is very high. Now, just try to define, what means a high input resistance in terms of few tens or few hundreds of megohms. That's a very large impedance. What that means that we are creating, using, this configuration. You notice that the non-inverting input is connected to the ground. Means that the inverting input, it will create a virtual ground. Why it's created a virtual ground? Because of the high resistance or very high resistance between the two inputs. Again, we'll discuss, about the input impedance for inverting amplifier or a non-inverting amplifier. But at this point, remember that the input impedance between the non-inverting and inverting input is very high. Means that the inverting input we are creating, or there is a virtual ground due to a very large impedance or very high impedance between the two inputs, the inverting and the non-inverting input. Now, I mentioned that in the op-amps, we don't have, to use, or, everything that we used before. The KVL, KCL is not applied in the same way, has, a different behavior. And one of these equations or one of these rules and laws for it's apply, in this situation or in this configuration for an inverting amplifier. Remember that if the current is flowing into a junction, has to be split into the other two currents. But again, we mentioned that, the current that flows into the non-inverting amplifier, due to a very high resistance between the two inputs, it will make the current that is going into the inverting input as equal to 0. Means that we are creating a virtual ground, or it's called a virtual ground or a zero level at this node. Means that the entire current that flows into this junction is actually going through the resistance RF. Means that we can make, the two currents having, the same value. Means that there is no current that flows into the inverting input. Means that the entire current that is provided by the voltage source or by the V-in goes through the resistance Ri, and the same current flows through the resistance RF. Means that that's, the observation that we are starting of before we are defining actually what is the gain of the op-amp. Now, knowing that, the two currents are the same, and again, is due to the very large or very high input resistance or input impedance of the op-amp, we can define, or we can use, the two currents, and we can define the input current, the I-in, as the input voltage divided by the resistance Ri, because again, that's, the zero or the virtual ground or the zero voltage or the reference voltage as being zero at this node. On the other way, or on the output, knowing, the output voltage is equal with the RF multiplied by IF. Means that we can define the IF as the negative V out over the RF. You notice that the current has, the same direction as is provided by the supply voltage or the input voltage. And using, the observation that we made before, the input current is equal with the IF, which is the feedback current. Having, this observation at the beginning and defining the two currents, we notice that we can make, the gain for an inverting amplifier. That's, the gain, the AC closed loop, because there is a feedback network. The bracket for I is for an inverting amplifier as the V out over V in. Having, those two equations, you notice that the two currents, being the same, we can find that the gain for a closed loop inverting amplifier has a negative RF over Ri. Remember that, has, that negative voltage, because actually, the current flows in opposite direction, because the inverting input is the same with 0 volts or the virtual ground. That's why you have that negative sign in front of the RF and the Ri. Now, the meaning of that negative voltage, and that's very important to understand, the negative voltage. I know it's a ratio of the two resistances, the RF over Ri. But that negative voltage is showing that the output voltage is out of phase with the input voltage, and the angle of this phase shift between the input voltage and the output voltage is 180 degrees. In lab, we determined that if we are applying a positive voltage on the input, we are getting a negative voltage amplified by a certain gain defined by the two resistances, and we'll end up with a negative output voltage. In reverse way, suppose that we are applying a negative voltage on the input, we'll end up with a positive voltage on the output, and the gain of this output voltage, it's defined or it's determined by the ratio of the two resistances, the RF and the RI. Now, make the difference between the gain for a closed loop for an inverting amplifier that has that negative sign in front of it, and the gain for a non-inverting amplifier. Again, non-inverting amplifier has no phase shift between the input voltage and the output voltage. As the input voltage is a positive value, the output voltage will be a positive value. And in the same way for a negative value, the input being, a negative value, the output will be a negative value. You notice that there is no negative sign. Always the gain for a closed loop non-inverting amplifier will have a positive value greater than 1. For an inverting amplifier, we can have always a negative gain, or the value of the gain for a closed loop circuit for an inverting amplifier always has that negative sign in front of the ratio of the two resistances. Now, using the same example that we used before. Suppose that we have the RF 82 kilo ohms and the RI as 3.3 kilo ohms. The gain for a closed loop circuit for an inverting amplifier is negative 24.8. You notice that always the gain for a closed loop circuit for an inverting amplifier has the negative sign in front of the dimensionless number. You notice that again, ohms and ohms are simplified and we have just the ratio of the two resistances. Means that using a negative gain, and I mentioned that before, we can have a precise gain or a precise amplification of the input signal. Now, based on the resistors, we can use a precise resistors, for example, 2% or 1%, and we end up with a very precise gain that we may use for the circuits, for the applications. Now, next step is trying to define the input impedance and the output impedance for an inverting amplifier. You notice that if I'm trying to go back and define the virtual ground or 0 volts, means that the input or the inverting input of the of the op amp is actually grounded, which is actually a virtual ground connected on the inverting input. And if I'm looking, into, suppose that again, I'm looking, from the source point of view into the circuit, which has the op amp and the external resistors, you notice that the RI is actually grounded, or it's connected to a ground. Means that what I am seeing, looking, from the source point of view into the circuit, I'm seeing, the resistance Ri only. Means that the inverting amplifier does not have that large input impedance as a non-inverting input, and the input impedance can be approximated with the Ri, or the input resistance that is connected in series with the supplied voltage. Now, in terms of the output impedance, you notice that the output impedance has almost, the same configuration as the non-inverting amplifier. Means that the same equation or the same expression or the same value of the Z out for an inverting amplifier is or a non-inverting amplifier. is the Z out or the output impedance of excuse me, the output impedance of the operational amplifier divided by, the same bracket, 1 plus the gain for an open loop multiplied by the B, which is the attenuation. Basically, the same equation or the same expression can be used to determine the output impedance for a non-inverting or an inverting amplifier. The only difference will be on the input impedance, which is much smaller than provided by the manufacturer. It's way much smaller compared with the non-inverting input impedance. That's why some restrictions is using the inverting amplifier applications, and you will see where we are using an inverting and or a non-inverting amplifier. I mentioned that, and I put in a short approximation. The input impedance for an inverting amplifier, it's almost the same with the RI or the input resistance. The Z out, it's the same with the output impedance for a non-inverting amplifier. And I put a note that emphasize, that both, circuits, the inverting or the non-inverting amplifier shares the same equation. Now, the other two topics is about, the compensation technique. Now, most of the time we discussed about, the zero output voltage if the two inputs are connected to the ground or one of the two inputs is grounded. In this equation or in this first circuit, you notice that that's a negative, that's the inverting amplifier. In this circuit, you notice that the input voltage is applied to the non-inverting input, and there is no feedback resistance or network between the output and the input. And the other one, which is the basic of the non-inverting input. In any of these cases, if the input voltage is equal to 0, or the input voltage is equal to 0, or it's grounded, we should have an output voltage as being equal to 0, and this is what we are looking for. That's the ideal op amp. Or most of the time we are not having a 0 voltage. It will be slight above or below the 0 voltage, but not always it's a 0 voltage. Again, we are amplifying the difference between the two inputs. If the V in is equal to 0, the other voltage should be 0, and the output voltage will be equal to 0. Again, it's the imperfection, it's the real values. If we are trying, to make, the identical resistors, there is a small difference between the two input transistors. We discussed about the input circuit of the op amp. Okay, we discussed about differential amplifier. Always there is a small difference between the two transistors or between a set of input transistors. Means that even if we are trying, to make this the same transistors, the same resistors, a small difference will cause the output voltage not being 0. Again, ideal should be 0, practical is not 0. Now the question is how we can compensate this imperfection for the circuit, and they come up with two solutions. One solution is always, using a small resistance, which is called the compensating resistance. That's, the RC. You notice that the compensated resistor. The RC having the value of the RI, which is in parallel with the RF. If we are trying, to compensate, the two resistances, the RI is parallel with RF, we can end up with having, a zero output voltage if the two inputs are connected to the ground. For an inverting amplifier in the same way, suppose that, the V-in is grounded, and we can see that the RI is connected to the ground, the output of the op amp is connected to the ground through the RF, means that the two resistors connected in parallel to ground, means that the RC, a small value of the resistance that has the value, the ratio of the two resistances, the RI and the RF. Again, it's not very practical because we have to have a precise resistance for the IC. I may end up with 2 or 3 decimal places or significant digits for the RC. It's not an easy way to find a precise resistance. Can be 0.1%, 0.01 or 0.05. That's a very precise resistance. It is not always available. Again, that's one possibility, and is not a practical arrangement or a practical solution for nullifying the offset in the biasing currents for the input stage of an op amp. A practical solution is using the pin 1 and 5 and connect a potentiometer. Actually, it's a very small potentiometer, which is called a trimmer. Now, if I'm going back to the introduction on this course, and I'm on this topic, you notice that I said that the pin 1, for example, is the offset knob. What this pin does, again, not always it's used, because not always is necessary to have the output voltage to 0, but in some precise applications, suppose that we are using a very small signal, which it will make a pretty large change in the output voltage if we are not making the output as 0 if the two inputs are connected to the ground. The pin 1, you notice that is called the offset knob, means that I can use the pin 1, and you notice that in this diagram is using pin 1 and pin 5. Usually the value of this potentiometer or trimmer is given, or it's provided by the manufacturer. Usually it's 5 to 10 kilo ohms, or 20, 25 kilo ohms, probably not larger than that, and it's connected to a negative of the voltage source, of the supplied voltage. And that's a very simple basic configuration. By simply adjusting or compensating the biasing of the input state, will make the output voltage of 0 if the two voltages are not connected to any voltage sources, or if I'm connecting the two voltage to the ground of the circuit. That's another possibility. In both ways, we can end up with an output voltage of 0, and this is how we can compensate the imperfection of the practical of the real op amp, or the real 741 operational amplifier. Now, another topic at the end, of this lecture. I was introducing the product between the frequency and the gain. Now, just to clarify again, where and what is the range of the applications in terms of the frequency. If we are plotting, the response of the op amp for a wide range of frequencies, we'll end up with, so-called body plots, or the frequency domain, or how the amplifier, or how the op amp, it will behave as the frequency is increasing or decreasing on the given range. You notice that the highest range probably is about 1.2, 1.5 megahertz, but the highest gain, which is called the mid-range gain, is just 10 hertz. Means that if I'm having an applied voltage or an input signal greater than 10 hertz, the output or the gain or the output voltage, it will decrease by with the gain of the op amp. Now, in some application, you may not need a very high gain. That's the open circuit or the open loop gain. That's in terms of 10.5, 10.6, which is 106 dBs. Above this frequency, which is a very low frequency, I mentioned that is just 10 hertz. For any input signal or input voltage is greater than 10 hertz, the gain of the op amp, it will decrease by 20 dBs per decade. It's called the roll off, or a decrease in the gain by a value of 20 dBs per decade. I mentioned that we can have some other adjustments or some other benefits of advantages of using a lower gain. Suppose that I'm not using the op amp for the open loop gain or very high gain. Suppose that I will drop the gain to 1,000 or less than that. You notice that if the gain of the circuit or the gain of inverting amplifier, non-inverting amplifier, it's drop or it's lower, you notice that the bandwidth for the frequency for the input signal, it increased drastically from 10 hertz to 10 kilohertz. Suppose that I can go lower than that, and you notice that if the gain is lower, because it's a constant decay, a constant decrease in the drop in gain for the amplifier, I can get much higher in the bandwidth for the op amp. Remember that always, the gain and the frequency, or the product between the gain and the bandwidth, the gain and the frequency, it's a constant number. The largest gain is the open loop gain multiplied by the frequency, which is very small, or a very low gain, or a much lower gain for a largest frequency. Always, the product between the gain and the frequency stays constant. Now we can define, the two critical frequencies. You notice that that's the FCOL. That's the critical frequency for an open loop. Means that that's the maximum frequency for an open loop gain, or the maximum gain that can be used just for 10 hertz. Remember that. If we are lowering the gain for the circuit, for the closed loop, we'll end up with a higher critical frequency. And to remind you, the critical frequency, how we can define that. If there is a drop in the gain by 3 dBs, means that the drop in the gain by 3 dBs. That's, a very small drop in gain compared with a constant gain that may be obtained across a wide range frequency. You notice that the higher closed loop critical frequency is much larger than the critical frequency for an open loop. But again, always is a trade between the gain and the frequency. And that's, the application that may be used, using, the same, two resistors, 82 kilohertz and 3.3 kilohertz. Again, if we are looking to calculate the non-inverting gain of the circuit, or the closed loop gain for a non-inverting amplifier, and we'll end up with a positive value, 25.8. Now, I mentioned that the maximum frequency is around, or it's about, 1 megahertz. Now we are dividing the 1 megahertz over the closed loop gain. That's the gain for a closed loop. The circuit is non-inverting amplifier. That's 25.8. We'll end up with the critical frequency, or the upper critical frequency, as 38.8 kilohertz. You notice that as the gain is decreased from 200, for example, 200,000 to 25.8, the frequency or the critical frequency of the circuit is increased to 38.8 kilohertz. As a recommendation, if your circuit or if your design requires a wide range for the input voltage, most of the time we can use, two identical circuits that amplifies the useful or the input signal with a small gain. In this way, using a small gain twice, or sometimes, 3 times, 4 times in cascade configuration, we can end up having a very large gain and very large frequency for a very low gain. Now, if the frequency is not a concern, we may use a pretty large gain, but again, depends on the input frequency, or depends on the signal. The most important part is look always for a constant gain, and define or try to find what is the specs, or what is the requirements for the frequency of the input signal. If the input signal is just a DC or a very small frequency, we can use up to the maximum gain, that is a very large gain, about I would say 200, sometimes is or anywhere in this range, 100,000 to 200,000, which makes 105, 106 dBs. That's a very large gain. Now, any questions, comments, concerns? Next lecture on Friday, we'll discuss some other applications which actually are based on a non-inverting amplifier and an inverting amplifier. Any questions, comments, or concerns, please? If you don't have any questions, have a nice day. And we'll continue with the applications for the op amps on Friday morning.